Welcome dear learners. We are continuing quantum chemistry. In this module, we are focusing on quantum mechanical treatment of SP3 hybridization. The contents of this module are some salient features of hybridization, the SP3 hybridization, construction of hybrid orbital wave functions of SP3 hybridization and molecules with SP3 hybridization. So, this module is intended to SP3 hybridization and quantum mechanical treatment of SP3 hybridization. First of all, hybridization. As we know, hybridization is intermixing up of atomic orbitals, but hybridization is a hypothetical concept. It is a theoretical concept. By definition, hybridization is the intermixing of atomic orbitals of nearly same energy to get a set of orbitals having identical energy and shape. So, in the present discussion, we are focusing on SP3 hybridization. In SP3 hybridization, one s orbital and 3 p orbital take part in hybridization. Hence, the total participating atomic orbital is equal to 4, and we will get 4 sp3 hybrid orbitals, and these 4 sp3 hybrid orbitals must have identical energy as well as shape. And it should be noted that these 4 sp3 hybrid orbitals orient towards the 4 corners of a regular tetrahedron, and hence the resulting molecules will have tetrahedral geometry. Now, some salient features. In the previous modules, we already learned about some important salient features, and these are mentioned here for just remembering the salient features of hybridization. And the important features are: the number of atomic orbitals formed is equal to number of atomic orbitals which undergo hybridization. This point that we explained just now itself. And the second salient feature is the sigma bonds formed from hybrid orbitals are more stable than those formed with the pure orbitals. Consider the formation of hydrogen molecule. And the hydrogen molecule is formed as a result of the overlapping of 1s atomic orbital of first hydrogen with 1s atomic orbital of second hydrogen. So, here the sigma bond or covalent bond is formed as a result of overlapping of pure atomic orbitals. But if you are taking the case of the CH4 molecule, there are 4 CH bonds, and each CH bond is formed as a result of the overlapping between sp3 hybrid orbital of carbon with 1s atomic orbital of hydrogen. That means here there one hybrid orbital take part in chemical bond formation. Hence, the sigma bond produced in that case will be more stronger than that produced from pure atomic orbitals. Next point, hybridization invariably involves atomic orbitals of the same atom, preferably the central atom. We are always specifying hybridization with respect to the central atom, and we are considering atomic orbitals of same atom. Effective hybridization occurs only when the orbitals undergoing hybridization are of similar energy. This implies that the participating orbitals must have nearly same energy. Orbitals with a huge energy difference will not be effective in hybridization. The electronic charge in hybrid orbital is concentrated more in one direction, and as a result, it leads to better overlap with the orbitals of other atoms. Hybrid orbitals generally form either sigma bonds or contain lone pair of electrons. They will never form pi bonds. That is, hybridization will not lead to the formation of pi bonds. The stability of bonds formed by the hybrid orbitals is due to excessive overlapping of orbitals provided by them. Now, this is one of the important aspect. What is the need for hybridization? We are now going to illustrate the necessity of hybridization by considering CH4 molecule as an example. Now let us consider this CH4 molecule. The central atom is a carbon. Carbon is having ground state electronic configuration 2s2, 2p2, 2s2, 2p2. Whenever I am representing it as box-wise notation, the 2s orbital has a 2 electron and there are 3 2p orbitals, say 2px, 2py and 2pz, and there are 2 electrons. This is carbon atom arrangement in outer shell in the ground state. This is 2s, this is 2p. But in order to form CH4 molecule, the central atom carbon must have 4 unpaired electrons, because as per the valence bond theory, a covalent bond is formed by the overlapping of the half-filled atomic orbitals. So, in this molecule, in the excited state, one of the electron from 2s orbital is just jumped to 2p orbital. That is, carbon in the excited state can be represented like this. This is 2s arrangement and this case is the 2p arrangement. One electron is excited to 2p, so here there is one electron remaining and 2 electrons are already present. One electron excited from 2s is shown here. Now you can see the presence of 4 unpaired electrons. These 4 half-filled orbitals overlap with 1s orbital of hydrogen to form a CH4 molecule. That is the resultant, that is the formation of CH4 molecule. But if CH4 molecule is formed without intermixing of 2s and 2p orbitals or without SP3 hybridization, 3 of 4 CH bonds, 3 of 4 CH bonds have, these 3 have more p character because they are formed from 2p electrons, and this one have more s character because it is produced from 2s electron. But in CH4, it should be noted that all the 4 CH bonds are identical. They have same, more or less same bond dissociation energy and their arrangements are same. These 4 bonds are oriented towards the 4 corners of a regular tetrahedron. Carbon is at the center, hydrogen, hydrogen. The bond angle is the same and that is marked as 109 degree 28 minutes. And due to the identical nature of 4 CH bonds in the CH4 molecule, we must ensure one thing. That is, prior to the formation of CH4 molecule, the 4 orbitals of the central atom carbon, namely 1 s orbital and 3 p orbital, equalize their energy and shape through a mixing up. Such mixing up is termed as SP3 hybridization. SP3 hybridization. So, during hybridization, 1 s orbital and 3 p orbitals both have same different energy and different shape, will mix up together to get a set of 4 sp3 hybrid orbitals having identical energy and shape. So, 4 sp3 hybrid orbitals are now present after hybridization, after sp3 hybridization of carbon. These 4 sp3 hybrid orbitals overlap with the 1s orbital of hydrogen, resulting in the formation of 4 CH bonds with the same arrangement, with the same energy, and the molecule is identical in bond length. 4 bonds are identical and bond angles are same, and we will get a highly equivalent 4 CH4 molecule. That means without this hybridization, the arrangement will not be like this. Bond energy may be different, bond characteristics may be different, bond angle may be different. So, in a CH4 molecule, all 4 bonds are equally oriented with the same bond angle, same bond length, every parameters being identical, and this identical nature occurs only as a result of SP3 hybridization. So, mixing up of atomic orbital prior to the formation of molecule is necessary, and this illustrates the need for hybridization. Now, we are discussing the SP3 hybridization. SP3 hybridization, as the name indicates, it is the mixing up of s orbital, that is 1s orbital, and 3p orbital to form 4 SP3 hybrid orbitals. That is, in SP3 hybridization, there are 4 orbitals will take part, and as a result, 4 SP3 hybrid orbitals are obtained. This is the pictorial representation of SP3 hybridization. This is 2s orbital for convenience, and this s orbital is spherically symmetrical, and this is a combination of 3p orbitals, namely px, py and pz, and this picture simply represents the complete set of p orbitals, px, py and pz represent together here, and if px is considered, the lobe is along x direction, if py is considered, the lobe is along z direction, and if pz is considered, the lobe is along z direction. And here this is a group of 3 p orbitals, namely px, py and pz orbitals. So, these are 3 p orbitals, and this is 1 s orbital. They will mix it together to get to 4 sp3 hybrid orbital. And for convenience, a hybrid orbital must have a big lobe and a small lobe. So, 4 sp3 hybrid orbitals are arranged like this. These are 4 sp3 hybrid orbitals. Each hybrid orbital consists of one large lobe and a small lobe. That is the representation of a hybrid orbital. Whatever may be the hybrid orbital, the representation is like this. There is a large lobe and there is a small lobe. It should be noted that the maximum electron density is concentrated in the big lobe. This is the shape of the hybrid orbital. This is big lobe and this is a small lobe. Maximum electron density is focused in the big lobe. Therefore, the probability of finding the electron is negligible in the small lobe. That is, in this small lobe, the probability of finding the electron is minimum, or electron density is minimum. So, hybrid orbital has 2 lobes theoretically, one big lobe. In the big lobe, electron density is maximum, and in the small lobe, electron density is minimum, or there is minimum possibility of finding electron there in the small lobe. Now, each sp3 hybrid orbital has 25% s character and 75% of p character. This can simply prove like this. Here there are a total of 4 orbitals, out of which one is s orbital. So, 1 by 4 is the character of s orbital, or 25%. 1 by 4, 0.25. When it is converted to percentage, 25% will be this character, and the remaining 3 by 4 will be the p character, 3 by 4 will be the p character, and hence 0.75, that is equal to 75% p character. So, in sp3 hybridization, s character is 25% and p character is remaining 75%. After hybridization, the 4 newly generated sp3 hybrid orbitals combine in such a way as to give a tetrahedral geometry. This is very popular fact that a molecule exhibiting sp3 hybridization will have a tetrahedral geometry, and the bond angle, that is angle between 2 adjacent bond pairs, is 109 degree 28 minute, or theoretically 109.5 degree. The equivalent hybrid orbitals are directed towards 4 corners of a regular tetrahedron. This is a regular tetrahedral arrangement. This is a regular tetrahedral arrangement. 4 corners of a regular tetrahedron. For instance, if we are taking, this is the shape of the CH4 molecule, carbon is at the center, hydrogen, 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 hydrogen at 4 corners. CH4 molecule is a tetrahedral with the bond angle same, 109 degree 28 minutes. Now, on comparing the stabilities of 3 hybrid orbitals, say SP3 hybridization, SP2 hybridization and SP hybridization. It is revealed that SP3 is the least stable. How we can compare the stabilities of different hybridization? The answer is here. SP3 is the least stable. This is because the SP3 hybridization, it is having minimum S character. What about the percentage of S character in these three hybridizations? In SP3, the percentage of S character is 25%. In SP2 hybridization, the percentage of S character is 33.33%. In SP hybridization, the percentage of S character is 50%. So, least the S character, least will be the stability, because S orbitals are close to the nucleus and responsible for the stability. Higher the S character, higher will be the stability. So, whenever we are assessing or comparing the stabilities of SP3, SP2 and SP, it is clear that SP hybridization leads to high stability, then only SP2 and finally SP3 is the least stable. This is due to the decrease in the S character. In SP3 hybridization, S character is only 25%. Lower the S character, lower will be the stability. Now, construction of hybrid orbital wave functions of SP3 hybridization. That is, we are now looking on the quantum mechanical treatment of the SP3 hybridization. First of all, we have to construct the hybrid orbitals. It is clear that in SP3 hybridization, 4 orbitals are take part in hybridization. So, we have to get to 4 SP3 hybrid orbitals, and hence we have to construct 4 SP3 hybrid orbital wave functions. Quantum mechanics provide a fundamental framework for understanding the concept of atomic and molecular hybridization, which plays a crucial role in explaining the structure and bonding of molecules. The wave functions for the hybrid orbitals are obtained by taking linear combination of atomic orbital wave functions, angular part of atomic orbital wave functions. The wave function for ith hybrid orbital formed from the S and P orbitals can be generally represented like this. Phi I is equal to AIS plus BI PX plus CI PY plus DI PZ. So, this is simply linear combination. AI, BI, CI and DI etc. are called coefficients of linear combination. These coefficients can be determined from the following rules. The first rule, this already we just mentioned whenever we studied about the case of SP and SP2 hybridization. The first rule simply says that as a result of normalization, we can arrive at the conclusion AI square plus BI square plus CI square plus DI square is equal to 1. And also each hybrid orbital in the set of hybrid orbital must be orthogonal to each other. Such orthogonality leads to the conclusion that AI AJ plus BI BJ plus CI CJ plus DI DJ is equal to 0. And these two conditions are very important in evaluating the coefficients of linear combination. And finally, there is one more rule. The squares of the coefficients of any component atomic functions summed over all the hybrid orbitals in which it participate must be equal to unity. That is sigma I, AI square is equal to 1, where AI is the coefficient of S orbital. By applying these set of rules, it is possible to find out the coefficients of atomic orbitals to take part in hybridization. And the coefficient can be evaluated by taking up the following procedures. Choose a Cartesian coordinate and place one of the ith hybrid orbital along one of the coordinate axes, and as many as of the other orbitals are possible in the plane containing this axis and other coordinate axes. Since S orbital has a spherical symmetry, each equivalent hybrid orbital is a set of 1 by n of the total unit S orbitals distributed in n hybrid orbitals. Hence, if there are n hybrid orbital, the coefficient of S will be constant, and that is 1 by root n. The wave functions for SP3 hybrid orbitals. Now we can take CH4 again as an example, and here there are 4 SP3 hybrid orbitals, and each SP3 hybrid orbital can be represented or constructed like this. Let the first SP3 hybrid orbital is psi SP3 1. This I can mark like this. A1 2s plus B1 2px plus C1 2py plus D1 2pz. The second hybrid orbital wave function psi sp3 2 will be equal to A2 2s plus B2 2px plus C2 2py plus D2 2pz. The third function can be represented this. Third hybrid orbital wave function is like this. Psi sp3 3 is equal to A3 2s plus B3 2px plus C3 2py plus D3 2pz. And finally, the fourth sp3 hybrid orbital wave function psi sp3 4 equal to A4 2s plus B4 2px plus C4 2py plus D4 2pz. Hence, these are 4 sp3 hybrid orbital wave functions. Or simply, these hybrid orbital wave functions contain 4 and 4, that is, there are 16 coefficients to be evaluated, and whenever we are evaluating such coefficients and put it in the respective equations, we will get the wave functions for sp3 hybrid orbitals. And we are in a step to proceed with the evaluation of the coefficients of the hybrid orbital wave functions. The 4 sp3 hybrid orbitals are like this. A1, B1, C1, D1 are the set of coefficients in psi sp3 1. Similarly, A2, B2, C2 and D2 are those present in psi sp3 2 and so on. So, we have to evaluate a total 4 and 4, that is 16 coefficients. Now, we are going to evaluate the coefficients of atomic orbitals in hybrid orbital wave functions. First of all, it should be noted that s orbital is spherically distributed, and we know since s orbital is spherically distributed, A1 square equal to A2 square equal to A3 square equal to A4 square. Since there are a total of 4, the result will be equal to 1 by 4. Or simply we can say that A1 equal to A2 equal to A3 equal to A4 equal to 1 by root 4, that is equal to 1 by 2. If a system having n hybrid orbital, the coefficient of s orbital will be 1 by root n. Ai's are the coefficients of s orbital, and here there are a total of 4 hybrid orbital wave functions, so n is equal to 4. So, coefficient of s orbitals, namely A1, A2, A3 and A4 will be equal to 1 by root n, that is 1 by root 4, that is equal to 1 by 2. Now, assume that psi sp3 1 point towards the x-axis. Now, we can just take a psi sp3 1. We know psi sp3 1 equal to A1 2s plus B1 2px plus C1 2py plus D1 2pz. And now we are taking the assumption that psi sp3 1 point towards x-axis. What happening if psi sp3 1 is pointed towards x-axis? Since it is pointed towards x-axis, it will not have any contribution from y or z component or Cartesian coordinate. Hence, the hybrid orbital will have a contribution only from 2s and 2px only. No contribution from y-axis or z-axis. That simply means that the coefficients C1 and D1 will be equal to 0. Therefore, psi sp3 1 can be simply represented like this: A1 2s plus B1 2px. The coefficients C1 and D1 will be vanishes. Since it is placed on, psi sp3 1 is oriented along x direction. Now we are taking the normalization condition of psi sp3 1. Since the psi sp3 1 is normalized, we can arrive at this point. a1 square plus b1 square plus c1 square plus d1 square is equal to unity. But we already proved that c1 square and d1 square or c1 and d1 equal to 0. Therefore, that two term vanishes and finally we are arriving at this result. a1 square plus b1 square is equal to 1. On solving that, b is equal to root of 1 minus a1 square. But we already know that a1 is equal to 1 by 2. a1 equal to 1 by 2, that is the coefficient of s orbital. By putting this value a1 square here, we will get the value of b, not b, but b1 equal to root of 3 by 2. So, we got two result, a1 equal to 1 by 2 and b1 equal to root of 3 by 2. With the help of that, we can write the expression psi sp31. Psi sp31 is equal to a1 2s plus b1 2px. a1 is equal to half and b1 is equal to root of 3 by 2. So, half 2s plus root 3 by 2 2px will be psi sp31. By applying similar mathematical procedures and applying the conditions of orthogonality, we can also derive the find out the coefficients for other hybrid orbital wave functions. Since psi sp3 is orthogonal with other 3 and c1 equal to d1 equal to 0, we can write some other relations. It should be noted that psi sp31 is orthogonal with psi sp32, psi sp31 is orthogonal with psi sp33 and psi sp31 is orthogonal with psi sp34. Also c1 and d1 equal to 0. This leads to three major equations. a1 a2 plus b1 b2 is equal to 0. This is as a result of the orthogonality condition between psi sp31 and psi sp32. The second equation is a1 a3 plus b1 b3 is equal to 0. This is as a result of the orthogonality between psi sp31 and psi sp33. Finally, this relation is obtained as a result of the orthogonality between psi sp31 and psi sp34. So, by combining this equations and proper substitution, we can get b2 equal to b3 equal to b4, or on simplification we get the value of b2 is equal to minus 1 by 2 root 3. Now, assume that psi sp32 is in the xz plane. What is expression for psi sp32? Psi sp32 is equal to a2 2s plus b2 2px plus c2 2py plus d2 2pz. Assume psi sp32 is in the xz plane. So, it is here, 2pz is also here, but it is not the plane containing no y-axis. So, the coefficient C2 is equal to 0. Hence, this orbital will have a contribution from 2s orbital, 2px orbital and 2pz orbitals. 2pz orbitals. It will not have any contribution from 2py, so coefficient C2 is equal to 0. Assume that psi sp32 is normalized such that a2 square plus b2 square plus c2 square plus d2 square is equal to 1. But we already proved that c2 is equal to 0. So, we arrive at the result a2 square plus b2 square plus d2 square is equal to 1. And the unknown parameter is d2. We know the value of b2 already and a2 is constant, that is 1 by 2. By substituting the values of a2 and b2 in this expression, we are getting the coefficient d2 is equal to root of 2 by 3. We know the orthogonality set relation between psi sp32 and psi sp33, psi sp3 and psi sp34. We are again getting two set of relations, that is a2 a3 plus b2 b3 plus d2 d3 is equal to 0. a2 a4 plus b2 b4 plus d2 d4 is equal to 0. That means we are getting the relation d3 is equal to d4 and we are getting the value of d3 equal to d4, that is equal to minus 1 by root 6. Also, psi sp33 is normalized. This is the normalization condition and we can evaluate C3 as 1 by root 2. On processing in the same way as that of psi sp3 4 is normalized and psi sp3 and psi sp3 4 are orthogonal, we are again getting the coefficient C4 is equal to minus 1 by root 2. By getting all the coefficients available, we get the complete 4 hybrid sp3 hybrid orbital wave functions like this. Psi sp3 1 is equal to half 2s plus root 3 by 2 2p. Psi sp3 2 is equal to half 2s minus half 2px plus root 2 by 3 2pz. sp3 3 is equal to half 2s minus half 1 by 2 root 3 2px plus 1 by root 2 2py minus 1 by root 6 2pz. And finally, psi sp3 4 is equal to half 2s minus 1 by 2 root 3 2px plus 1 by root 2 2py minus 1 by root 2 2pz. These are the 4 sp3 hybrid orbital wave functions. You can see that A1, B1, A1, A2, A3, A4. These are the coefficients of s orbitals. All are same here, that is 1 by root 10, that is 1 by root 4, that is equal to 1 by 2. This is about the hybrid orbital wave functions for sp3 hybridization. Now we are considering molecules with sp3 hybridization. We are now illustrating some examples. We are considering some molecules with sp3 hybridization. We are considering some simple molecules. First of all, we are taking the case of methane. In methane, the central atom is the carbon atom. It has 2 unpaired electrons in the ground state during excitation. As I mentioned in the case of the CH4 molecule, one of the electron from 2s is just excited to the 2p orbital. So there are 4 unpaired electrons in the excited state. The energy required for the excitation is satisfied by the energy released during hybridization. All the bonds in methane are sigma bonds which are formed by head-to-head or end-to-end overlap of hybrid orbitals of carbon with 1s orbital of hydrogen atom. The geometry of the methane molecule is a tetrahedral with a bond angle of 109 degree 28 minute or 109.5 degree as shown here. Another example is ammonia molecule. In ammonia molecule, the central atom nitrogen has 3 unpaired electrons. 1s and 3p orbitals of nitrogen molecule combine together to form new sp3 hybrid orbitals, 4 sp3 hybrid orbital. One of the hybrid orbital is completely filled with the lone pair, whereas other 3 hybrid orbitals are half filled or partially filled. These half filled orbital overlap with the 3 1s orbitals of the hydrogen atom to form NH3 molecule. The bond angle in ammonia is not 109 degree 28 minute, but there is a slight diminishing, and that slight decrease from 109 degree 28 minute to 107.5 degree is as a result of lone pair bond pair repulsion, which can be explained on the basis of valence shell electron pair repulsion theory. This is the geometry of the ammonia molecule. Here we can see the presence of a lone pair which is in red shade as shown here. The bond angle is 107.5 degree, and the shape of the molecule, we are cutting the lone pair whenever we are explaining the shape of the molecule. If that lone pair is removed, this ammonia molecule is having a pyramidal shape, but geometry is same. If hybridization is constant, hybridization is same, geometry is constant. So ammonia molecule is having tetrahedral geometry with the one position occupied by lone pair, and the shape of the molecule is simply pyramidal. Another example is water molecule. In water molecule, oxygen is the central atom. It has 2 unpaired electrons. However, out of the 4 hybrid orbitals obtained, 2 are completely filled with the 2 lone pair of electron and 2 half filled orbitals. These 2 half filled sp3 hybrid orbitals on oxygen atom overlap with 1s orbital of 2 hydrogen atom to produce 2 OH bonds, and water molecule is produced. The oxygen undergoes sp3 overlap, hence it forms 2 sigma bonds with the hydrogen atom. The 2 hydrogen atom occupy 2 corners of a tetrahedron, whereas the remaining is occupied by lone pairs of electron. There are 4 corners, out of which 2 corners are occupied by hydrogen atom and 2 other positions are occupied by lone pair. The molecule geometry is simply tetrahedral, but the shape of the molecule, if we are excluding this lone pair, the shape of the molecule is bend or V shape, but the bond angle is again decreased from ammonia, and the bond angle is 104.5 degree. This can also be explained on the basis of the VSEPR theory. Thus, by this discussion, we have considered the entire quantum mechanical aspects and quantum mechanical treatment of sp3 hybridization. with relevant examples. That all about the present module. Have a nice learning experience. Thank you.